So, welcome to the class. We will start the discussion of special theory of relativity. And as we know, in physics, we are dealing with either motion or rest. And you know that this motion and rest are not absolute. According to you, if someone is at rest, that means suppose you are traveling in a bus, the person sitting near to you is at rest according to you. But for an observer who is standing on the road, who is observing the passing of bus, according to him, the person which is who is sitting near to you is in motion. So this motion and rest are not absolute, they are relative. And this concept is an olden one. But our olden concept of relativity was not the same as nowadays we are using. Now we are using the concept of relativity by Einstein, and the olden concept was the Newtonian concept. So we will start with some terms in relativity, and we will initially discuss the Newtonian concepts, and there we will discuss what are the drawbacks of the treatments there, and then we will go to the Einstein concepts. So in a relativity, that means classical relativity, a theory of relativity is in effect a way for observers in different frames of reference to compare the results of their observations. And in the example, uh, a passenger in bus, so according to the traveler in the same bus, uh, his frame of reference is that bus itself. And for a person standing in road, so he is standing in the road, so his frame of reference is different. So their observations are different. According to one, the a particular passenger is stationary or rest, and the person standing in road, he is in motion. So according to those different frames of reference, their results is different. Their results are different, or the result is different simply. So how you can compare that results? And the theory of relativity is in effect a way for observers in different frame of reference to compare their results. And for example, uh, you can consider an observer in a car parked by a highway near a large rock. So to this observer, the rock is at rest. And another observer who is moving along the highway in a car sees the rock rush past as the car drives by. To this observer, the rock appears to be moving. That means moving backwards, or you can say. And these two pictures will give you the idea. And this is the car at rest. So, according to him, the rock is at rest. And this is a passenger who is passing away. And as he moves away, the rock is rushing backwards. So, he is or she is looking backward for that rock. The theory of relativity provides the conceptual framework and mathematical tools that enable the two observers to transform a statement such as rock is at rest in one frame of reference to the statement rock is in motion in another frame of reference. So, in relativity, we will connect these. That means both observers are actually they are correct. According to their view, they are correct. So, this relativity provides some conceptual frameworks and mathematical tools to transform one point of view into other. And more generally, relativity gives a means for expressing the laws of physics in different frames of reference. So, the mathematical basis for comparing the two descriptions is called a transformation. So, you are transforming from one view to other. Figure shows an abstract representation of the situation. Here, you have two observers, O and O dash. That O stands for the term observer. Observe the same event. O dash moves or O prime moves relative to O with a constant velocity u. So, this is your frame of reference O, which is at rest. And this is moving with the velocity, and you are marking it as O prime or O dash. And that the same thing, your rock or anything else, according to the observer at O, he is observing, and so it has a particular place in space with respect to him and at a time. That is why it is marked as x, y, z and t, or x, y, z and t. And for moving observer, it is x prime, y prime, z prime and t prime. Two observers O and O prime are each at rest in their own frames of reference. And this is important. They are at rest in their own frame of reference. That means if one passenger is moving in car, according to car or with respect to car, he is at rest. But the car itself is moving. So you are considering that car as a frame of reference. And a man standing in road, and according to him, the man is at rest. For that road or with respect to earth, he is at rest. Two observers, O and O prime, are each at rest in their own frames of reference, but move relative to one another with constant velocity u. O and O prime refer both to the observers and their reference frames or coordinate systems. They observe the same event which happens at a particular point in space and a particular time, such as collision between two particles or whatever may be. And according to O, the space and time coordinates of the event are x, y, z and t, while according to O prime, the coordinates of the same event are x prime, y prime, z prime and t prime. The two observers use calibrated meter sticks and synchronized clocks. So, any differences between the coordinates of the two events are due to their different frames of reference and not to the measuring process. So, we are trying to measure the events. We simplify the discussion by assuming that the relative velocity u always lies along the common x prime direction as shown in figure, like this. So, along this direction it is moving. So, this x prime is the direction of u. Let u represent the velocity of O prime as measured by O, and thus O prime would measure velocity minus u for O. That means, suppose you are considering this x prime as the direction. This is we are normally taking as the positive direction. So, this O prime is moving with the velocity u with respect to O, and this O is moving with the velocity minus u with respect to O prime. That means it is moving backward. In this discussion, we make a particular choice of the kind of reference frame inhabited by O and O prime. We assume that each observer has the capacity to test Newton's laws and finds them to hold in that frame of reference. For example, each observer finds that an object at rest or moving with a constant velocity remains in the state unless acted upon by an external force. And this is your Newton's first law or the law of inertia. Such frames of reference are called inertial frames. That means both these observers find that, according to them, Newton's first law is valid. That means an object at rest or moving with a constant velocity remains in that state unless acted upon by an external force, and this is our Newton's first law. And such frames are called inertial frame, means such frames where your Newton's first law is valid, you can call them as an inertial frames. So this is the definition. An inertial frame of reference is one in which the Newton's first law of motion holds good. And all frames of reference at rest or moving with the constant velocity relative to another inertial frame of reference are also inertial frames of reference. This is an important concept here. All frames of reference at rest or moving with the constant velocity relative to another inertial frame of reference are also inertial frames of reference. That means we are saying that if O, our frame of reference, is an inertial frame, then O dash is moving with a constant velocity relative to O. That means this O prime or O dash is also an inertial frame. So you have to remember this definition of inertial frame. An observer in interstellar space floating in non-rotating rocket with the engines off would be in an inertial frame of reference. That means he is at rest there. So you can say that it is an example for inertial frame of reference. That means either it must be at rest or it must move with the constant velocity. And what about the accelerated frames? An observer at rest on the surface of the earth is not in an inertial frame because the earth is rotating about its axis and orbiting about the sun. That means it is in a circular motion or elliptical motion, whatever may be. There it is experiencing a centripetal acceleration. That means it is an accelerated frame actually. So an observer at rest on the surface of earth is not an inertial frame. That is actual concept. But at space, the rocket is at rest and no force is acting on it, or it will be at rest, or it will be moving with the constant velocity. Then it is an inertial frame. But however, the accelerations associated with those motions, that means motion of earth around sun, are so small that we can usually regard our reference frame as approximately inertial. So normally you are considering as our frame of reference is inertial, but actually it is not. But more or less we can consider it as inertial frame. An observer in an accelerating car, a rotating merry-go-round, or a descending roller coaster is not in an inertial frame of reference. So if a car is moving constantly from us, with a particular velocity, you can say that that is also an inertial frame. But if it is accelerating, it is not an inertial frame. And you know this term merry-go-round that you can normally see in exhibitions, and a descending roller coaster, which you can see in the theme parks like this. So this is the go merry round. So it is going round. So there, these children are experiencing an acceleration. So you can say that they are not in an inertial frame of reference. And here you can see the roller coaster. This is the roller coaster. And when it is moving from here, the top to bottom, it is an accelerated motion under gravity. So you can say that this is not a man sitting here or a woman sitting here. So you can't consider them as an inertial frame. And here also you can see that this will be moving with acceleration. And this is known as your giant wheel or fairy wheel. So these are or are not examples for inertial frame, and you are calling them as non-inertial frame. So a non-inertial frame of reference means accelerating and uniformly rotating frame of reference are called non-inertial frames of reference. Actually, if it is uniformly rotating, though it is with a uniform angular velocity, it is experiencing acceleration. That is why its speed and angular velocity may be constant, but there it is experiencing acceleration. That is why you are saying that accelerating and uniformly rotating frames of reference are called non-inertial frames of reference. And now we will consider the Newtonian principle of relativity. If Newton's laws are valid in one frame of reference or in one reference frame, then they are also valid in another reference frame moving at a uniform velocity relative to the first system. And this is referred to as the Newtonian principle of relativity or Galilean invariance. That means Newton's laws, which are valid in one frame, is valid in other frames or in another frames. They are moving with the constant velocity with respect to the first. That means Newton's laws are invariant. That is why you are calling them as the Galilean invariance. And this principle, that means if Newton's laws are valid in one frame, it is also valid in other inertial frames. This is known as the Newtonian principle of relativity or the Galilean invariance. And the classical or Galilean transformation, now we have to discuss. The classical or Galilean transformation that relates the coordinates x, y, z and t to x prime, y prime, z prime and t prime. We have already mentioned that this x, y, z, t as the coordinates with the reference to the frame of reference O, and this x prime, y prime, z prime, t prime with respect to O prime. And this O prime is moving with a constant velocity with respect to O. We assume as a postulate of classical physics that t equal to t prime. This is the concept of classical physics. That means here t means an instant or time interval. More correctly, it is a time interval. So, from the stationary frame of reference, if you are observing something and if it is happening in say 1 hour, the same thing if you are observing in a uniformly moving velocity frame of reference or another inertial frame of reference, you will feel that same time interval as, that means that same process as it is happening in the same time 1 hour. That is why you are saying that t is equal to t prime. That is, time is the same for all observers. This is the concept of our classical relativity. For simplicity, we assume that the coordinate systems are chosen so that their origins coincide at t is equal to 0. So, initially both are at the same point, and then as time lags, the moving frame of reference is moving like this. Initially, this is here, they are at the same points. So, as time lags, this is moving to this, that means in the x prime direction, x prime direction with the velocity u. Consider an object in O prime at the coordinates x prime, y prime, z prime. So, this is an object with the coordinates say x prime, y prime and z prime. According to O prime, the y and z coordinates are the same as those in O. So, which is moving only along the x-axis. That means here also we can say that according to this O, if you are observing this, so this is the value of x here, and this is the value of z here, this is the value of y here, and this is the in O prime, this is the value of y, and both values of y are same, and here this is the value of x, z, this is the value of z, both are same. But here the value of x is x prime, that is only this value, and from here the value of x is this much. So you can say that the y and z coordinates are the same for O and O prime. Only there is a change for x and x. And along the x direction, O would observe the object at x prime equal to x plus ut. So initially this was here at this point. It is moving with the velocity u, and in a time t, the distance it can travel, you have the equation velocity or speed is equal to distance by time. Distance equal to velocity into time. That means in a time t, with the velocity u, it can travel a distance u into t. So in a time ut, it can travel this distance ut. So this you are considering as x prime. And according to O, this is the position that you are considering as x. And according to O prime, this is the position that is x prime. So you can write as x equal to x prime plus ut. This is the equation. You can again observe that figure, and you can verify this equation, x prime equal to x plus ut. Therefore, we have the Galilean coordinated transformation. That means you have the equation x is equal to x prime plus ut, and actually you are writing one side x prime, other side x. So you can write as x prime equal to x minus ut, y prime equal to y, z prime equal to z. And already we have mentioned as t prime is equal to t. And this you can mark as equation number 1. And to find the velocities of the objects as observed by O prime and O, we take the derivative of these expressions with respect to t prime on the left and with respect to t on the right. So, on the left side, you have the prime coordinates. So, there you have to use t prime, and in this side, you will use t. And again, you are saying that we can do because we have assumed t prime equal to t. In normal sense, suppose you are differentiating an equation, you have to differentiate with the same variables on both sides. That means both the left hand side and right hand side. But here, for the left hand side, you are using t prime and right hand side t, because t and t prime are same. That is why you are using like that. And this gives the Galilean transformation as, you can write as dx prime by dx prime, dx prime by dt prime, that you can consider as the velocity vx prime, and dx by dt will give you vx, that means velocity along x-axis. And here this u you are considering as a constant value, so u is a constant, and differential of t with respect to t is 1, so it is just minus u. Vx prime is equal to vx minus u, and vy prime, that means dy prime by dt prime equal to dy by dt, that you can write as dy prime by dt prime as vy prime, dy by dt as vy. Similarly for z as vz prime equal to vz. So this is the velocity transformation equation. This is the coordinate transformation equations. Similarly, you can have the equation for acceleration. We can take the derivatives of equation 2 with respect to time and obtain relationships between the accelerations. That means ax prime equal to ax, ay prime equal to ay, az prime equal to az. Here you can see, you can take vx prime by dt prime equal to vx by dvx prime by dt prime, you can take as ax prime equal to dvx by dt, that you can take as ax, and here this u is a constant, so differential is 0, and here it is easy, you can understand. So we got the equations as ax prime is equal to ax, ay prime is equal to ay, and az prime equal to az. And this equation 3 shows that Newton's laws hold for both observers. That means acceleration is same in both frames of reference. As long as u is constant, du by dt is 0. So the observers measure identical accelerations and agree on the results of applying force is equal to mass into acceleration. So they are feeling the same force because acceleration is same in both frames of reference. And now, by considering these transformation equations, you can have some problems, and I think we can do it in the next lecture, and we will be starting with this lecture. So before the next lecture, I request you to have a copy of the textbook, and it will be provided. So